Welcome back. Today we're talking about using limits in basically what amounts to a calculus situation. And we're talking about using limits to evaluate slope at points and tangent lines, and really ultimately starting to look at what does it mean to have a derivative. And so that's what we're going to look at today. So as we look at this, um, let's start off with an example that we looked at just a little bit, but we're going to explain it a little bit more to kind of drive that point home. Use limits to find the slope of the tangent line to the graph of s equals t squared. So this is our s of t is equal to 1, 1. And so this is going to actually be the t that we're evaluating it at. So we're going to use that x like it's the time, like it's the t. And so as we talked about, we're really looking at the limit as t approaches 1 of our change in our s over our change in our t. And so that's going to look like this. It's going to be our function evaluated at t minus our function evaluated at 1 over t minus 1. And so we have the limit. And like I said, this sometimes is the hardest part is writing this limit over and over and over. T squared minus 1 over t minus 1. And so essentially, remember, as we were talking about, if we put in 1, it looks like we're dividing by 0 because we're trying to find that instant. We're shrinking that interval to where the interval is so small that we're finding an instantaneous velocity, right? And we are relating that to the slope of the tangent, like the instantaneous velocity is the slope of the tangent line. But we can't divide by 0, and so these limits take on this algebraic feel because I'm trying to factor them so that I can have something that I can actually use to evaluate the point, right? And so if I factor it, look at what happens. All of a sudden I can cancel out this t minus 1 over this t minus 1. So the limit as t approaches 1 becomes t plus 1, and that's where I put in my 1 for my t. So the limit equals 2. So the slope at that line, at that point, is equal to 2. Okay, so that's kind of how this works. So we're going to do the same thing down here. The slope of the graph, so we want to use limits to find the slope of the graph of the function at the indicated point and the equation of the tangent line at the point. And so let's take a look here. So let's first use the slope of the graph, find the slope of the graph at the point. So we're going to do the limit as t approaches, in this case, -1 of 2x squared minus 2 times -1 squared over t minus a minus 1. So this equals the limit as t approaches -1. Oh, and feel free, if you're comfortable with this, go ahead and pause it here, and you can try it and then come back and see the answer. So this is going to be the limit of 2x squared, and this is going to be minus 2 over t plus 1. Okay, so let's kind of take a look here. I've sort of started mixing my variables, so I need to switch this over to t. That's my fault. Okay, because essentially it is x, it takes on the x value, but it's t because we actually are talking about time and that instantaneous velocity. So let me rewrite here. The limit as t approaches -1 of 2t squared minus 2 over t plus 1. And I'm going to, again, understand that if I put a -1, it'd be divided by 0. And so I need to do some factoring. So up top, I'm going to take out a 2, and I'm going to have t squared minus 1. And then a t plus 1, and I think you see what's going to happen here. So we have this difference of squares that can come out. So the limit as t approaches -1 of 2 times t plus 1, t minus 1, and t plus 1. So then these plus 1s can cancel out. So the limit as t approaches -1 is 2 times t minus 1. And so what happens is I put in my time that I do have in for my t. And so the limit as t approaches -1 is 2 times -1 minus 1, which is -4. Okay, so how do I use that? Well, that's the slope at the point, so I need to find the equation of the tangent line at the point. And so that's going to look like this. So the equation of tangent at point is equal to this. Well, so I have a point, right? Or I can have a point. I have this x value. So the point is -1 comma 2 times -1 squared, right? Because that's my function. So I put an x to get my y value. And so that's going to be -1 comma 2, right? And so my equation at the point is, and I can use point slope form here. So I have y minus 2 equals -4, that's my slope, times x plus 1. So y minus y1 equals m times x minus x1, and I put that into my point. So I could put this into any form asked for. I could put it into point slope form, I could put it into slope intercept form. So that's the equation of the line at the point, because the tangent line, or the slope of the tangent, is found by taking what's going to amount to the derivative, but it's using the limits to find it, okay? So go ahead and pause here. Try this one. When you come back, I'm going to do it, and so you can see if you got it right. All right, so we are after the pause, and I'm looking at the limit as t approaches 2 of 2t minus t squared minus 2 times 2 minus 2 squared over t minus 2. So let's look. And again, as you hopefully are now starting to get the gist of, we're hoping that we can find a way to cancel some stuff out up here. So if this is 2 squared minus 2, that's 4. So this is 2t minus t squared minus 0. Well, that's good. T minus 2. And I need a t minus 2 at the bottom. Well, you kind of see in here, I've got this like, I could factor out a t. So the limit as t approaches 2 of t times 2 minus t minus 2. So they're flip-flopped, which means I need to factor out a negative. So here we go. The limit as t approaches 2. And if I factor out a negative, I've got negative t times t minus 2 over t minus 2. And so that limit, when I put in my x value, so this is my time I want to evaluate, remember that's my 2 here, as it goes to 2, these are canceled out, so my limit as t approaches 2 of my change in my position over my change in time is equal to -2. This is my slope, right? That's my slope of my tangent line. And so the slope of my tangent line is found by getting that instantaneous rate of change. And so I'm going to put that into my point slope form. Okay, so if this is my f of x, right, equal to 2x minus x squared, f of 2, because I need a point, right? I need to get a point for point slope form, and I only have the x. So I'm going to do f of 2 is equal to 2 times 2 minus 2 squared. Which, like, Mr. Sarich, you just did that right here. I did. So I did find what the y, essentially the quotes y value is right here. And so I know that my point is slope is equal to -2. The point is 2 comma 0. And so I put that information together to say y minus 0 is equal to -2 times x minus 2. So y equals -2 x minus 2. Okay, that's it right there. That's how you find that tangent, that slope of that tangent line, and you can use that to write an equation of the line at the point. Okay, average rate of change. So the average rate of change, this is all kind of summing it up. So the average rate of change is my change in y over my change in x, which is equal to So check out what this is. The average rate of change on an interval is the amount of change in y over change in x, slope, hello, so f of b minus f of a over b minus a. Well, think about what this means. This is my x1, this is my x2. I define the interval using interval notation as from some x value to some x value. Well, the change in y is, this is y2, right? Because that's the function evaluated at b. And then this is y1, and so those are super messy. Sorry about that. So this is y2 and y1. This is actually a formula that we've done before, right? Except we just wrote it a little bit differently. Well, this is derivative at a point. So the derivative is written like this: f prime of a. So this means derivative. So the f prime of a is equal to the limit as x approaches a, so some value x, which is what we were just doing, of f of x minus f of a over x minus a, okay? Which is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Well, Mr. Saris, what are you talking about here? Well, what I'm talking about is f of x minus f of a, x minus a. That's what we just did with the t's, right? Except now I'm talking about x's. So this is me shrinking my interval, talking about the amount of change in the y values, amount of change in the x values over a really small interval. Well, this is how you shrink the interval to an infinitesimal amount. I'm going to say h equals 0. So this down here represents change in my x. It's close to 0. Equals small interval. Right? So over a really small interval, I'm measuring the amount of change from f of a plus h to f of a. Well, what does that mean? This is my change in y. When the y values are close together, meaning f of a and f of a plus h is getting really small. So we're finding this really small interval to find the amount of change over. That's how we're going to find this instantaneous velocity. Okay? And so essentially, watch what happens here. This f prime of 4, if f of x is equal to 2x minus 3, looks the same as those other examples. So f prime of 4 is equal to f of 4 plus h minus f of 4 over h. Well, what does it mean? It means I'm using now this definition of derivative, which is essentially the same thing we were doing before when we had the t minus my value. Except now I'm just saying I'm evaluating this interval for f of h plus 4 and f of 4, which makes it really small because h is going to 0. Okay, so this is actually f prime of 4 is actually equal to, and we have to have the limit notation in here, the limit as h goes to 0. Well, what's it look like? So we'd have the limit as h goes to 0 of 2 times 4 plus h squared. I'm putting it into this function here, minus 3. And all of that, now I know it looks complicated, stick with me. Minus 2 times 4 squared, minus 3. And all that's going to be over h. So this is where that algebra comes in handy. And I told you that calculus sometimes looks like a lot of algebra, and you got to be really proficient at it. And so we're going to have 2 times, and I'm going to expand this right away. I've got h squared plus 8h plus 16 minus 3 minus, and then this amounts to, so this would be 2 times 16 should be 32 minus 3 minus 29 over h. So I've got limit as h approaches 0 of 2h squared plus 16h. Okay, I'm expanding this now. And then plus 32 minus 3, right, would be plus 29 minus 29 over h. Are you seeing the value of algebra here, folks? Are you seeing it? And so I'm going to step to the side here because this is the limit as h approaches 0 of 2h squared plus 16h. These two cancel out over h. Well, watch, look. This is awesome. The limit as h approaches 0 of h's cancel out. 2h plus 16 over h. Nope, my h went away. Okay, and the limit is equal to 16. Okay, it's equal to 16 because I did the algebra and I manipulated it and everything canceled out. That's the limit. That's the derivative as it approaches that h equals 0. Okay, so everything works out, and that's the derivative at the point. This is the slope at 4. Okay, that's the instantaneous rate of change at 4. That's how derivative works. Now you're going to find a shortcut for this in calculus, but I'm trying to get you to understand before you go there that this is exactly how it works. Okay, this is exactly how it works. It's finding the instantaneous rate of change by shrinking an interval around a given x value so that you can determine exactly how much change there is over a very tiny interval. I want to make a quick change here. I don't want you to evaluate it at 2. I want you to find the derivative at 1. Okay, so the derivative at 1 of 1 over x plus 2. So try this, do it. When you come back, I'm going to give you the solution. Okay, we're back. As we're finding this derivative at 1, I'm taking the limit as h approaches 0 of 1 over 1 plus h plus 2 minus 1 over 1 plus 2 over h. Now this is where it gets a little bit tricky because I got fractions inside of fractions, but this is your algebra skills coming out, right? So the limit as h approaches 0 of 1 over h plus 3, and it's going to get less complicated here, minus 1 over 1/3 over h. If I step to the side here, I've got this fraction minus a fraction here, so I need a common denominator. So my common denominator is going to be 3 times h plus 3. 3 times h plus 3. I multiplied this one by 3, so this is going to be 3 over 3 times h plus 3. This one's going to be h plus 3 over 3 times h plus 3, and I'm subtracting those. So take a look at what I got here. That was just a common denominator situation. It's all still over h. So the limit as h approaches 0 of, now I'm going to combine these. I've got 3 minus 3 would be just a minus h left over 3 times h plus 3. And so when I look at this, I'm still dividing by h, right? So all of that on top is still over h. And so when I step to the side here, I'm going to do the limit as h approaches 0. Now this is a general thing. This happens a lot, and this is something that students often forget, is I'm still dividing by h. So this is essentially h over 3 times h plus 3 times 1 over h, right? That's what dividing by h means. You're multiplying by 1 over h. Well, watch what happens here, folks. You're going to love this. Boom, gone. Boom, gone. So, as I look at this, I'm looking at the limit as h approaches 0 of negative 1, because the h is canceled, over 3 times h plus 3, which is equal to the limit as h approaches 0 of 1 over, now h is now 0, shrinking to 0, negative 1 over 9. So the limit equals 1 over 9. That's my slope at my point, okay? So some really, really, really heavy algebra in this point. So if you can do algebra, you guys are going to be golden for this. So just keep track of where your variable's at and remember what you're doing, and things are going to start to cancel out, and you're going to be solid to evaluate the derivative at those points. Okay, guys, thanks for watching, and we'll see you next time.